Welcome to Building Resilience, How to Be Firewise, where we'll be hearing about how we can design to reduce the risk of wildfire in our communities and learn about the ways in which high performance design and resilient design overlap. In other words, how do we create one design to optimize safety, health, and efficiency? We have a large registration list here again tonight, and we're very glad that you could join us. CGBG is a Boulder County-based nonprofit organization founded in 2004 that brings together builders, designers, product manufacturers, engineers, real estate professionals, you name it, that are committed to or interested in green building. We are here to provide resources, education, and networking opportunities to our members and provide leadership in the community. Although we're a small organization run by volunteers, it's been amazing to see the amount that we've been able to accomplish over the last few months as we dedicate this year to assisting where we can in the recovery and rebuilding of communities impacted by the Marshall Fire. And on that note, I want to reflect something that I learned through many conversations at the Boulder Valley Build Expo last month and in dozens of email threads that I've had since. Many homeowners tell us that they don't want to become and don't have the time or energy to become building science experts in addition to insurance experts, code experts, FEMA experts, and all the rest. We hear you, and we hope that through this event and many more like it, CGBG can be a resource that you can point your chosen professional, building professionals to seek out. Ultimately, that's our strongest hand to play in this collaboration. And our purpose is to provide resources and connections to building professionals all across the Front Range with the intention of helping us all learn and grow. For those with ideas on how we can be of greater service in this regard, please let us know. Please reach out. You can do that through our website. We want to hear from you about ways our expertise in green building can be used in the work that needs to be done. So with that, we're moving on to thank our sponsors that help us make this work happen. Our sustaining sponsors include Louisville's own Alpin High Performance Products, who have been a national leader in window technology, as well as 475 High Performance Building Supply, which is the company I work for. We provide building materials as well as free educational resources for architects and designers. Our supporting sponsors are Hammerwell, Design Build, Caddis Collaborative, Living Craft, Boulder County, Cottonwood Custom Builders, and Florist Systems. And yeah, special shout out to Living Craft for becoming our new sponsor on this list. We have many great upcoming events on our calendars. A few that I would especially like to share. CGBG members, EMU Systems, a team of local Passive House trainers and consultants are hosting a Passive House happy hour and expo for building professionals in person in Arvada on Friday. This event occurs each time EMU is offering their Passive House design course. CGBG will have a table there along with several of our sponsors and other industry professionals. Excel will be hosting a virtual event partnering with Colorado Energy Office to discuss the 2021 IECC residential code updates. That's happening March 23rd. This is a part of a monthly series of providing. And our next event is March 29th, when we'll welcome back one of last month's panelists, Brian Fuentes. This will be a virtual walkthrough tour of a recently completed Passive House project in Louisville by his firm, Fuentes Design. They will share details on how this home was accomplished for under $350 per square foot. This presentation is primarily directed to building professionals and will include very technical details that enable the successful execution of passive house projects. So homeowners and others interested are definitely welcome by all means, and they're encouraged to share this information about this event with their professional teams that they're working with. All of the event details and registration pages can be found on our event page. Let's drop the link into the chat now for that, cgbg.org/events. The best way to continue to stay up to date on the latest is through social media, our newsletter, or by visiting our website. However you prefer to stay tuned, that's where you'll find us. These here at Instagram, Facebook, YouTube, and the email registration link which you'll find at the bottom of our website. Lastly, before we begin, we'd like to thank AIA Colorado for making this presentation eligible for continuing education credits. For those who are architects, we'll be dropping the link in the chat now where you can fill this form out to receive those credits. For those of you who will be passing this presentation recording on to your architect, you see the link on the screen now. That's what they can use to utilize those credits. And we'll remind everyone of this again at the end. One more reminder, I think a few of you here may be having trouble. If you have to choose the language selection, regardless of what language you want to listen to, there's the language selection icon. It's at the bottom of your Zoom window, bottom right. We're going to show the image here again now. That globe icon is what you need to select and choose one language or the other. Once you do that, you should hear it just fine. So without further ado, we'd like to introduce our presenter, Andrew Michler. Andrew has focused on high performance building design and materiality since 1993. He is an author, the co-founder and current board member of Passive House Rocky Mountains. He has served as a chair on the Northern Colorado Renewable Energy Society. He completed the first internationally certified passive house in Colorado in 2016, for which he's won several awards, and also for which, as you see here on the screen, if you type passive house into YouTube, it's one of the most watched passive house videos on YouTube, period. That's how a lot of people meet him for the first time. And so thank you, Andrew, for joining us this evening.
Great, thanks for the introduction, and thanks for the embarrassing shout out for that YouTube video. It is kind of funny. But if you don't know Kirsten Dickerson, she does for a good 12 years now. She's traveled the world with her family in tow, just filming some of the most awesome projects in the world. I don't know how she does it. So honestly, 1.7 million views is that's kind of medium amount of views she gets. She's extremely popular and she does brilliant work. So it's neat to see that. Yeah, I do live here. I've been here in Colorado for maybe 26 years, 27 years. I've been off grid for 25 years. And I live out in the foothills, the wildlands urban interface, off grid. And so I've been thinking in Ponderosa Pine Forest, I've been thinking about fire resilience pretty much since 1991 when my family's house burned and we went to refurbish a used house, an existing property. That's when I first learned about building and how important it is, and I've been interested in ever since, especially on the fire resilience side. So tonight I want to start off a little bit about what carbon in buildings is as a reference point to a lot of the conversation we're going to have. This is not an isolated event, this fire, and in fact, Cameron Peak fire came creeping right up to the edge of my property a couple of summers ago, and we're going to see this over and over and over again. So we really have to think about kind of the built environment and in interaction with kind of the greater environment, so to speak. I'll get into Firewise design, which is kind of the main topic tonight, of course, and then talk more about resilience and passive house and how we need to talk about building as a system rather than just as components when we talk about building in 21st century conditions. And as you probably know by now, Xcel Energy is offering pretty generous rebates for higher performance buildings over code. I'll focus mostly on passive house because that's what I know best. And that also integrates better or best with kind of this Firewise or this resilience context. Just kind of from the broad view of what buildings mean in the greater environment is they're about maybe in the mid 40% of the total atmospheric carbons. And that comes from the building operation, meaning the energy it takes to heat and cool them and to operate them, running lights, equipment, things like that. And then another large chunk is the building materials and construction. And that's becoming an even larger and larger number over time, and something that people are honing into as well. I won't get into the building and materials side of it, but I will focus a little bit on the energy side of it today. And just a kind of frame of reference on what that means is year one is when most of what we call embodied energy, typically for a building, takes place in the materiality of the construction. And then over years is when the operational energy, the carbon input comes from. And so even as our grid gets cleaner, it's still a slow transition, a slow ramp to hopefully a zero carbon or low carbon energy infrastructure, but that's going to be generations away, unfortunately. So our main focus now is on the energy side of buildings from that perspective. So first thing we look at is eliminating fossil fuels on site and then reducing demand for energy in general. That starts with the high performance building envelope. And then reducing demand for methane gas or natural gas upstream, which means we're still using power, but we're using less of it when it's produced by what we call peaker plants or natural gas fed plants. The all electric home means that we're going to be heating, cooling, hot water, and even cooking is going to be all electric. And the technologies now are here that are fantastic and are highly subsidized as well by the utilities. Roofs are oriented or built for PV, and you're now thinking about not just use of the building itself, but car charging as that becomes electrified. But we're building neighborhoods. We should think of our cities or neighborhoods not as giant solar plants, but we should also think of them as accessible, green, biodiverse living places. So we don't want just to build giant flat roofs for PV. We really want to create more compact housing that can include a diverse, biodiverse environment. In terms of the Firewise home, the kind of interesting perspective I found on this website, Wildfire Today, was that researchers discovered that in 2008 or newer, the homes are about 16 percentage points or 40% less likely to be destroyed than 1990 home experiencing identical wildfire exposure. And that has to do with the change in code over time in specific regions in the country. I'll talk a little bit about that, but also we should be certainly advocating or looking at the conclusive evidence that fire resilient design is extremely effective and not necessarily more costly than traditional code buildings. And I'll tell you why, is because exterior fire events are typically not well considered in code. Usually we're looking at, like, just for fire resilience, we're looking at maybe a 5/8 inch drywall between the house and garage if there's a fire in the garage, protect the house. Unfortunately, like insulation is usually not fire rated. Smoke alarms, or it's not, or not particularly strongly fire related in the type of insulation you can choose. Smoke alarms, firewall blocking between floors is pretty typical. And now we're seeing often a Class A fire roof is used in a lot of areas. But typically, when we're looking at light framed wood construction or single family residential, fire is not a particularly high consideration for code compliance. So it's pretty much on our own how we want to think about how to create fire resilient homes in the future at this point. And I used this analogy before and with the help of Johnny, and I'm going to kind of reuse it again, is the idea of thinking like a log. And we often have, I'm sure most of you have tried to start a campfire or a wood stove fire, and you know the first rule is you just don't throw a log in and put a lighter to it. Usually start with kindling, and then you build up to the log. So part of that is because of something called the surface area of the materials. Much easier to start when you have lots more surface area on a given object. So that means we start the design considerations with buildings with a more simplified design. And that includes porches, that includes kind of the vernacularisms of the building as far as portals or corners. All sorts of things can lead to increasing the fire exposure of the building. So simplifying that form greatly improves its fire resilience. And here's a nice set of drawings that kind of show what happens during a fire event. This is from Colorado State Forest Services created a few years ago, a great pamphlet PDF that you can look up for Firewise construction. And so you're looking at places for embers to collect within the building, around the building, on top of the building. And they even mentioned solar panels, which I found was really interesting. So for instance, like these Tesla solar panels, not to endorse a specific brand, but it was nice to see that they wrap their solar panels so embers can't get underneath and then into the shingles nearly as easily, for instance. And then very broadly, removing materials around the house specifically that can lead fire directly to the structure. Wooden decks, unfortunately in Colorado, we love to live outside. Wooden decks are a perfect way for a fire to really capture underneath the deck, on top of the deck, and then transition right into the house. Wood fences, landscaping, again, porches, kind of all sorts of little detailing around a house that's combustible. So we call that the home ignition zone. And this is more of a WUI, wetlands urban interface kind of construct. So very, very suburban is where this started, but now we're starting to see it in more of a neighborhood scale, and as well as individual houses. And often we find that one house will lead another house to burn. So protecting neighborhoods becomes a critical element in fire resilient design. And you can see from that photograph to the right how extraordinary fire resilient neighborhood can respond to a fire event. And if you see all these houses, they're all stucco tile roofs, somewhat simple shapes. You don't see any wood fences or anything like that. So we're seeing extremely improved fire resilience through individual building design, landscaping, and neighborhood design. So this means fire landscaping. This means the first few feet of your house is the most susceptible for fire resilient or for fire to start. So kind of hardscaping that, so to speak, or putting in plantings that will not support fire. Landscaping becomes critical within the next 5 to 10 feet or so, even 15 feet away in a fire event. So that's something that you want to be doing. Selective planting is on, keeping grass, things like that, well kept, cutting grass when it's dry, things like that, and having good good overall design and interface between kind of that greater area around you and your dwelling. When it comes to the dwelling itself, this idea of mind the gaps, often with fires, the first thing that comes is this ember front. And those embers are pretty sneaky. They'll go where the wind blows. The wind will blow anywhere it wants to, or it can get into. And that often means places like eaves or underneath crawl spaces that aren't protected, things like that. So the first place that we look to within the building itself is protecting eaves. Unfortunately, this is part of where code has not been helpful at this point for protecting of eave design. We do advocate for trying to have a fully insulated roofing system or a fully encapsulated roofing system to eliminate the possibility of hot air and for embers to get into. There's other issues that can come with that if it's not properly detailed as far as like moisture control, things like that. But in the case of a fire, that's kind of the first place we look to is eave design. And then windows. Second thing that comes is this large heat front. And we've seen this in the mountains over and over again, where people build like a concrete house or a real kind of fire resilient structure. But the windows themselves were the first thing to go in a fire front. What happens is that high heat, radiant heat, can expand the glass and crack the glass. So I've heard numbers like 5 minutes, 3 to 5 minutes of high heat can crack a single pane of glass. So you can imagine once you have 2 panes of glass that your house is essentially open to the entire outside environment, and you have a completely unprotected interior. So we're looking at triple pane glass, which is also tempered, 3-way tempered. Typically is much higher performing in a fire event than what a typical double pane glass would be. And that also includes how the frame is built, like a tempered glass with an aluminum frame on the exterior can help stay more rigid than, say, a vinyl type of frame. And then, of course, once the fire is around the house itself, having fire resilient materials is critical. So sadly enough, and it kind of breaks my heart that wood exteriors are becoming less and less prominent because of this out in the West here. You can imagine how easy it is to start a cedar shake wood siding. Certainly can't do it on your roof, but now even looking at wood can withstand radiant heat quite well, but it can't stand direct heat very well, or flames, I should say. So the good news is that there are a ton of options out on the market now, either mimicking wood or vernaculars that are, maybe a little bit more modern, a little bit more traditional, maybe a mix. But we have a good variety from steel roofs, from these are called Class A materials, I should say. So from stuccos to brick to fiber cement. Cement boards are becoming quite popular. There's even architectural cement boards that look quite modern, not like a traditional lap. Stones, things like that. So when you're looking at redesigning a house, there's quite a great experience in discovering these types of materials, and even the cost effectiveness is pretty good now, especially with the fiber cement products. But it's more than skin deep. We should look at how the walls are assembled as well. And this means starting with foam. Foam is particularly, even with what they call fire resilient agents in them, they still tend to burn extremely well. Spray foams and board foams. And they're used ubiquitously, both in normal code built houses and quote unquote high performance houses. So we're looking at eliminating them within the building structure. And unfortunately, fiberglass is the most popular of all insulation materials, but it's typically quite airy. It lets air through the material itself. So it doesn't take much to get a fire going inside of a cavity with a fiberglass insulation and for it to spread as a result. So kind of the preferred, two of the more preferred measures to look at that are mineral wool board and mineral wool bat, which is becoming much more mainstream now. Mineral wool is very popular because it has a high R value per inch relative to fiberglass, but it's also extremely fire resilient, almost to the point of being fireproof. And surprisingly, cellulose insulation, which is recycled paper product, what that does is that's called dense packed. So it doesn't allow air through the cavity, and also has a fire retardant that can smolder but doesn't support flame. So I'll go quickly into my own house as an example of like what a highly fire resilient assembly might look like. And I'm going to start from the outside in. Is that this even though it looks like wood, this is just Hardy Board brand material. So this is fiber cement. There's a little bit of wood accent right there. I threw some rock out in front. I should definitely trim grass, but that first barrier is to keep fire embers from having any place to perch and for very little material to actually be able to burn. Underneath that, of course, I have steel in the back of the house as well. Underneath that is a mineral wool board, and that's the exterior insulation material. And 2.5 inches of that makes a completely fireproof boundary zone, essentially, for any fire that catches right next to the house. Inside of that is a substantial amount of cellulose insulation, and then a structural wall, which has a mineral wool bat in it. So this is a very fire resilient assembly, and then the triple windows, and then protected frames for the windows. So that's my particular approach that I took my house, and there's lots of different ways to look at assemblies. I wanted to also emphasize that when we look at kind of the idea of resilient design, we also want to talk about surviving fire events, even if they don't necessarily go right up to our doorstep, but the air quality issues and especially smoke issues, which have can be a substantial problem, both for health and essentially, contaminating the house to the point where it's unlivable, as unfortunately a lot of people have found out. So we're also looking at the idea of air pollutants in general. Ozone, as you unfortunately probably know, that Colorado's ozone levels have been defined as extreme last summer. And it's not getting better, unfortunately. We're seeing a lot of smoke from just the west from fire events, all the way from Canada, Vancouver, all the way to Southern California, zeroing in right into the Front Range here. So we're seeing this as a very typical event, is air pollution on the exterior as being a condition for resilient design. So that means that we need to look at, best case scenarios, that we look at the building envelope as a airtight envelope. And that means right now code has buildings typically at 3 air changes per hour is how they test it under using what we call blower door. But we want to be actually a lot more airtight than that. That's completely insufficient for keeping pollutants out. And I'll show you a graph of why that is. So we'd like to look at dedicated air barriers within the building itself. And this goes hand in hand with some other aspects, which I'll get into later. And once you get a very tight building envelope, you're going to want to look at a dedicated ventilation, fresh air system. So we're taking this build it tight and ventilate right. This is the concept of taking that to its kind of logical conclusions. This is, as we know, in Australia, they've been going through extreme Victoria area. They've been going through extreme bushfires in the past few years, and a lot of homes have burned. So they're looking more and more at kind of adaptive design for fire resilient conditions. And they found out that passive house airtightness is one of the kind of the key ingredients now that they're recommending for fire resilient buildings. There's a lot of other kind of detailing that they are taking into that's more of a kind of a wildfire condition in a backcountry environment, but the airtightness is kind of a universal for all of us now. And that's going to jump into me getting a little into more of the passive house side. Of course, I've been thinking and working in passive house for a long time, so I use that pretty much as a reference. And I'm using the reference in this talk is that we need to look at buildings as systems and not as individual components. Components don't necessarily add up to a totally resilient building condition. So using passive house methodologies is a framework to look at the idea of looking at resilience as a system. And in the terms of passive house, what we're talking about is 21st century kind of concepts around what shelter is. So 19th century, we just put a lot of BTUs pushed through a building that had minimal insulation. 20th century, we added a little bit more of insulation, but we were recognizing that we had to put lots and lots of more heating and cooling equipment in. In fact, we probably wouldn't live the way we do now without air conditioning, for instance, or build the way we do now. We've been subsidized by complex equipment and energy as a result. So in the 21st century, we're looking at kind of envelope design and improving the envelope, both in the amount of insulation, the level of passive solar, and the fresh air systems. So you can think of it as like a thermal battery. And here's a kind of a quick idea of what the outcomes are for passive house compared to what a code building is, as far as like energy input and the losses for a building. So we're reducing the amount of losses so we can deeply reduce the amount of input of energy compared to even like a low energy house is what the Passive House Institute would refer to as. And I'll start off with a personal story on why this is important in the terms of resilience. Get a drink of water here. Something called the Passive House Challenge was set off about a year and a half ago. And it was a strange coincidence that I had a couple of artists, mixed artists who are both visual and musicians, write an album in my house back when we had that big cold front, the famous one that wiped Texas out pretty much. And for us, that was the coldest I've ever been. I think it was -19 for a few days and didn't get above 0 for at least a week Fahrenheit. And sure enough, my pipes froze coming into the house. The house didn't freeze, but the pipes coming into the house froze. And the genius I was had to use my hot water heater as the heating source for the passive house. So I ended up not having a heating source. And these guys trying to write an album in the house had no heating during this Arctic front, record Arctic front for me, at least. And for them, they never complained. And finally I said, so how are you guys doing? They're, oh no, it's a little bit chilly, but we're doing great. It was 57 degrees, I think is the lowest it ever got into that house with no heating for about 6 days. So to me, that's the epitome of resilience, is a building that can be quite livable and even borderline just a little uncomfortable, but very reasonable with such an extreme event, both cold and not having the heating during that cold event. And that story, Jeff Conley was able to tell that story during a TED talk about kind of what passive house means in the terms of many of the qualities of it. And resilience is right up there on the top. And this happened right at the time that they were trying something called the Passive House Challenge, where people were on purpose turning off their heating systems for a week and measuring their passive houses. So kind of the characteristics of what we're looking for to get to that level of resilience with extreme weather events is the high performance continuous thermal envelope. High performance windows and doors, certainly. Thermal bridges are eliminated, and thermal bridging is kind of the way the heat escapes through materials that are connected from the outside to the inside that are conductive. That can be steel, can be wood, things like that. Even the frame of your windows can be a substantial heat loss. Airtight building envelope, as I talked about, and then the ventilation system, heat recovery. These are kind of the core considerations of this type of building process. Kind of the early examples of where Passive House started from, with the first original Passive House completed in 1991, I believe, in the lower right-hand side. And just I threw this slide in to show that they're everywhere and at every kind of scale. So it's nothing exotic. It's not particularly strange. It's designed for all sorts of different environments. And I'm going to circle back and talk about that form factor we talked about earlier about the fire resilience, think like a log. That's called the form factor. And it's also something that we consider in Passive House as the heat loss form factor. So you can imagine like when you have mittens where your fingers are completely covered, you are reducing, of course, the surface area from your hands and they're covered. So your hands will be much more or much less susceptible to cold environment. Once you have a glove that's just fingers, then each finger is going to radiate more surface area, be able to radiate more heat. And then, of course, thermal bridging or something where there is no insulation is where we're directly connected to the outdoor environment, which is not good. So here's kind of an example of what that can look like just from a raw calculation from a heat loss point of view. It's a little sciencey, but this is how we start designing these kind of resilient high performance homes at the very beginning, is that every time we increase the surface area, we need to also increase the level of insulation. And we can do that through a parametric design. We do that through energy modeling. The air tightness side is where we want a dedicated air barrier through the building, and then we can test that. And typically for code, we test air tightness after the building is built. That's crazy. We don't test things after you do them, you test them while you're building them. So often with the dedicated air barrier, we can also test the buildings to see how airtight they are during construction, so we aren't bury these problems. And these problems can not be just for particulates getting into the building and reducing the air quality inside the home, but they also protect from vapor, moisture coming from the outside into the inside, condensing on a cold surface potentially, and rotting the house from the inside out, or from vapor from the inside of the house. The high humidity in the inside wants to go to the outside walls. So it's a way to protect that as well. So in this case, we're looking at a 0.36 air changes per hour. So that's a good, maybe 5-6 times, actually 10 times more airtight than building code. And the more airtight you are, the better off you are, to be honest. And then on the ventilation side, we look typically now, code is a little bit cagey. They do require ventilation, but they don't often require balanced ventilation. And sometimes that ventilation is mixed with other systems. So it's not particularly well balanced. So we do like to look at well-balanced ventilation systems using energy recovery, heat recovery ventilation systems. And that gives us the opportunity to control how air is exchanged from the building. So we can extract air from the pollution sources like cooking or bathrooms and put in fresh air right into bedrooms and places of the living area. And in terms of kind of smart smoke particulate things, because of unfortunately, Australia's had so many fire events that they've been able to measure air particulates in extreme smoke events in Canberra, which is the capital of Australia. It's definitely just right in the middle of the country there. It's lots of burn areas around it. And the chart to the left is going to show the blue is going to be what they consider just a typical house or a leaky house. All houses in Australia are leaky. So they can just say house rather than just leaky house. Airtightness is not the vernacular there. And then when you look at the blue is outside the particulate matter. The red is a house interior for leaky house during that smoke event. And then a passive house is the yellow. So the passive house is maybe 30 or 40% better than what the leaky house is, but it's still letting in particulates using just a standard filtration system. So if you look at the chart to the right-hand side, we still have the red for the typical house, but the yellow in this case is a house where they use the HEPA filter on the inlet side of the dedicated ventilation system, and they're able to like dramatically reduce the amount of particulates in the building during that extreme fire event. So that's a good sign to show that we're still able to provide fresh air and healthy air even during these kind of really bad breathing conditions. And you can extrapolate that when air quality is quite marginal, how good the air can be inside the buildings with HEPA filter systems. Jumping to kind of where the energy side for the resilience side of it, for passive house at least, I'm going to do a quick uptick because you get $37,000 from Excel for rebuilding. So I want to just quickly talk about how passive house works in that context. Is it starts off with an energy modeling software called the PHPP. And that accounts for building losses, air exchanges, all the other things. And the intent is getting the base load heating down to essentially the size of what a hairdryer would be for a typical residential house, let's say 2,000 square feet or less. And then there's certification levels, and to get that rebate, you'll need to be certified. For passive house, there's the classic, plus, and premium, and those ones just kind of like if you don't use renewables. The other one is adding renewables to what we consider a net zero building. I'll put that in quotes. It's a complicated topic, but a net zero concept. And then premium for passive house would be for if you wanted to also extrapolate renewable energies for your neighbors, for transportation, for your vehicle plug-in, things like that, and sizing that accordingly. And this is all done through intensive calculations within that very, very elaborate energy modeling process. In terms of the team in passive house, we have what we call a certified passive house designer or consultant, and they'll be the architect or building designer. And then the consultant can either be the designer or somebody who works with the designer. The builders have a tradesperson's certification, and they are the ones who are getting tested on site and are implementing all these kind of measures. But they can't build something that's not designed for, like, say, an airtight environment in the first place. So that interaction between the architect and the builder is critical. As owners, we're pretty much the ones who are going to cheerlead this and make sure that everybody's up to task and keeping their part of that process front and center. And then there's a certifier for passive houses for making sure that everything's done correctly, documented correctly, tested correctly. And then there's commissioning specialists for, like, the ventilation system, or as we talked about, the airtightness system. Those are actually commissioned or tested on site. So you know that you know what you're getting. And then sometimes there's specialty consultants involved in these projects, especially around atypical building systems for thermal bridging, thermal dynamic analysis. Can get quite complicated quite quickly at times with more complex buildings. And finally, I'm going to end on a project we're working on now that foundations in Colorado Springs. And Colorado Springs has a pretty rigorous fire, in the city itself has a pretty rigorous fire code. And the fire code, of course, they've had entire neighborhoods burn on the West Hills, Colorado Springs. So they understand what that concept of is, like one house leading to another house, leading to another house scale fire event. So now they've been very strict on plantings around the buildings and on what we can put on the outside of the buildings. So the client asked for all wood, and we quickly found out that you can put no wood on the buildings, maybe a little decorative wood on a door, but that's about it. So we had to build a building that had no fire relatable materials on the exterior. But as we get kind of deeper into it, we can look at kind of how that simple shape also plays a role, kind of upping the game, so to speak, for fire resilience and in terms of passive house or low energy buildings. In this case, we're quite below what the passive house standard is, which is 15 kBTUs per square meter, is what we're doing in the metric system. We're at 9.6 for this project. But the project, even though my renders aren't fantastic to show exactly where it is in a fairly dense neighborhood of all sorts of different types of houses. We have a mix of stucco, some wood, lots of various kind of conditions in the neighborhood. So like that earlier photograph of that neighborhood where the fire stopped right in its tracks once it met the fire resilient, Firewise neighborhood design, this house is going to play that role within the context of this environment. For the fire protection of the house itself, we have metal roofs. We're using a fiber cement board to mimic lap siding, like a vertical lap siding on the exterior. The simplicity of shape makes it much more simple. Hardscape is going to be like a concrete patio down below, and a gravel drive around the house, surrounding the house. And then the decking is of non-combustible materials on top. The house is also going to be made from prefabricated panels from a company called Collective Carpentry up in Canada. We hope to have them set in late April. So this is basically the walls of the building, and the roof will be built in a factory and then set in site. So we hope that can weatherize the house within just a few days, for instance. So it's something new for us, but something we want to see a lot more of for the quality control aspect of it. And then there's a lot of talk about kind of the net zero part of this rebate, or the kind of the concepts around what we think of as green building, what Xcel Energy needs to target to for their production of energy for their long-term planning. And so what they really want to see is a relationship between the energy consumed and the energy produced. So energy produced means the solar panels on your roof, for instance. You're going to make peak energy during the summertime, but in the wintertime, if for a typical house, you're going to consume quite a bit of energy in this particular climate, especially in Colorado. Even if we put heat pumps into the buildings, we go all electric, all of a sudden we're going to have a significant demand for power when we can't produce it with renewable energy. So that means we still have to use natural gas, even coal plants, right? So we're trying to get out of that mindset. So we want to flatten that curve. So the first part is to reduce the energy demand. So there's still a gap, unfortunately, in the wintertime at this point. But as far as like energy production, that means we can also reduce the energy production for the buildings themselves. And if you want to produce more energy for the buildings in terms of net zero, we can either use less solar energy, less solar panels on your roof on site, or you can put more solar panels on, as we talked about, for your plug-in your electric car or your electric motor, whatever else you want to do with it. So we're reducing that gap substantially. And as technologies improve, especially around energy storage, which is still a long time off on the scales we need to talk about. That gap of energy storage during peak usage, especially in wintertime, is significantly reduced and even viable. I live off grid, so clearly I need to take that more quite seriously, but my battery system can suffice for 1, 2, 3, 4 days when I'm not producing energy to make a livable house. And go back to where we began from that large scale concept of kind of living on a planet, a resilient planet, let's call it, how our buildings connect with that in the energy relationship. Ultimately, we want to look at something called the primary energy renewable, how we can source energy through just not immediate use, but through time of use, through seasons, so that our buildings are responsive for when the renewables are produced and stored to when we consume them at the building site in our homes. So we look at the kind of the short-term storage solutions that connect with immediate renewable energy, and then more long-term solutions that can be complex. A lot of these are a long way out in technology, but they will be coming online. So we're almost talking about future-proofing our houses now for future primary energy renewable systems that will be slowly being integrated into the grid in the future. So, you know, for me, especially during this kind of wartime situation, if you look at Europe with what they're looking at for gas, when we look at Colorado, even especially around fracking, air pollution, we need to just eliminate our dependence on fossil fuels as soon as possible. And gas prices, you know, the list goes on and on for what we're seeing, immediate negative things that's happening to us personally, and more globally as well. It's really hitting us in the face at this point. So the idea of decarbonizing is as much for peace as it is for anything else. I'm going to throw out some resources. I know there's a lot of emphasis on the passive house within this talk, but I want to re-emphasize the idea of thinking as a building as a system. When it comes to resilient design, it's not just about electrifying our homes, but looking at kind of the total environmental conditions that we're building through a high performance envelope and equipment within the building itself. And that's a design problem. It's a construction issue, and it's a QA issue. It's something that we need to be able to test during and after the process. So here's some resources. I'm part of the Passive House Rocky Mountains group. We'll be working with Colorado Green Building Guild, I hope, in the future to provide kind of more in-depth information on a lot of these topics. And we'll also be providing trainings for tradespeople and for designers as well. And then I'm part of Hyperlocal Workshop and principal of that, do lots of passive house projects in Colorado and around the world, I should say around the States. And then the national organization is called the North American Passive House Network, or I should say the Passive House Network. They just recently changed their name. As far as like passive house materials, I just went through the website today again, and there's a ton of content for materials from very beginning to advanced level for these types of buildings. So at that, love to have a Q&A with you guys. Hope it wasn't too long, and thanks for your patience.
Well, thank you very much, Andrew. I wanted to first start off by mentioning that for those watching, because it's a webinar, you can't see the total number of people in here, but we did have a total of 370 people register, which speaks to the importance of this as an issue, and certainly we'll be utilizing this, you know, as a recording on our website. So yeah, thanks again for putting this all together. We did get a lot of questions, and for those of you who maybe haven't had a chance to think or put the questions, go ahead and put those in the chat. We do have these links here, and I did see the mention to say, hey, can we get the links that Andrew just put up on the screen on the site, and we will do that. So to start in on some of the questions, one that I think is pretty important to start with is why would you say, so in this, for instance, in this Marshall Fire event, homes that were meeting Firewise design or trying to meet Firewise design burned just like any of the other ones did. And in particular, they mentioned stucco homes they saw burned to the ground. And why do you think those failed? And in addition, is cement siding better than stucco? So first part being, why did we see that happen in this fire event, and what can we do better?
So that's a really complicated question. And I guess the first thing to say is we can't design fireproof buildings. We can only design fire resilient buildings. And Firewise is really the start of the conversation. As Prasad, I really want to emphasize that systems approach. So fire is extremely sneaky. It can come in really quickly. It can come in around the perimeter. It can come right up to your building, or it can come as a heat front. So you have to kind of anticipate all these other conditions. And there are times like on our mountain, we lost 11 homes, unfortunately, here. And it was just that even with limited amount of vegetation, the way that the fire was able to funnel through with the fuel conditions and the wind conditions, it just jumped. It came right through like a blowtorch. There probably are some particular designs that did well. I think windows was the one thing that failed first for a lot of buildings here. And then gutters, things like maintenance, having debris in your gutters, and then the debris gets up underneath. Even if you have a metal roof, if it gets underneath that roof, then it can slowly spread into the house itself. So it's a really complex problem, and it's something that almost code won't be sufficient at. So what we're doing is reducing the odds. We're not making a fire. It's like gambling. You're just kind of stacking the odds on your side when a fire event happens. And it's been hard to talk to people about that on my mountain, about that idea of odds. But we've seen it over and over again when people did more fire resilient buildings, that they definitely survived when houses around them did not survive. No, I think stucco, especially if it's on plywood or even a more fire resilient material, is probably similar to how cement fiberboard would work in terms of fire resilience.
So you think they equate relatively similarly?
Yeah, and there's actually fire testing now for residential, but for commercial buildings, you can get a fire rating for your wall systems, and that's when they do look at the entire wall assembly and components within that wall assembly for fire rating. So you can do a deep dive into fire rated wall systems.
And I think, correct me if I'm wrong, but kind of as you were alluding to in some of this, is it's not just your home, it's your neighbor's home, and it's your neighborhood as well. And in theory, like a whole neighborhood could be designing around some of these issues and strengthen as a whole, which I think would advocate quite well for the whole the HOA approach. I think we saw someone in the chat, John, mention I think an HOA, sort of maybe an entire community, which is what we have the opportunity to think about now, is how can a whole community design around some of these things. And
it's great to see Colorado Springs really take that to heart. Unfortunately, they did lose neighborhoods, but they witnessed that, and they just put an outright ban on. It wasn't a ban. It wasn't really a Firewise code. It's just like somebody said, get rid of wood. That's why these houses are burning. So they just banned wood. It wasn't necessarily based on like a full Firewise kind of assessment of a building, but it was a great start, and they integrate the landscaping in the building materiality and to do neighborhood protection.
This next one sort of different. We talk, of course, about incentives available from Excel for this event. Could you speak to incentives for builders to build energy efficient? Is there anything you found in your work that incentivizes builders?
It's more up to CGBG to know what that is. Yeah, it's incentivized builders. I think that's a good point. You know, let me incentivize it this way. And we've been thinking about this a little bit. I haven't actually done that, but for like, let's say the airtightness part of it, which is really quite rigorous. And Johnny, that you live and breathe the airtightness part of it through your company. And one idea I was thinking contractually is like contractually having your builders meet a threshold for the airtightness. If they achieve passive house level airtightness on the first or second round, then they get a bonus. But if they don't achieve it, then they have to pay you back because that costs you money because you put a significant investment into that. So I think you can't be dependent on, you know, kind of government agencies or outside entities, but it may be something you could consider putting in a contract.
Right.
You just scare your builder away. I don't know, but that's one approach of
literally incentivizing performance measures and things that are measurable and that you can test.
Yeah. And we find builders pick up on the airtightness thing really quickly. It's a fantastic. It's probably one of the best news cases of the high performance building field is how we can make these things super airtight.
Next one, can you speak to, and this is one we hear a lot, and as you said, I work a lot with airtightness. For those who, you know, learned lessons in the 70s that air exchange and, you know, letting walls breathe was very important because of the mold issues that moisture causes. And this switch to building airtight. Could you speak to that?
Johnny, I prefer you to, but I'll start. And if you want to riff, I'll start is that a lot of houses actually are subsidized. The reason why houses don't necessarily mold into mulch so quickly for traditional code built buildings is because we lose so much heat, it literally dries the house out. It's like putting your house in an easy bake oven. It just dries it out in the wintertime all the time. So what we're trying to do is not lose all that heat. And so in the 70s, what they did was it wasn't the air tightness that wasn't the problem. It was the fact that they didn't have a vapor control process and the science wasn't there. So we make lots of vapor inside the house when we cook and we live in a building, especially in the wintertime. And they didn't have a strategy for controlling how that vapor went through the wall. And it started condensing on cold surfaces in the building. And now we're very, very keen on vapor control. In Colorado, for instance, we won't use plastics. We'll use vapor materials that have a vapor profile that's vapor somewhat permeable. Sometimes you can get materials that can change vapor profiles when you want them to. It gets pretty geeky at this point, but we want to look at keeping the moisture from going into the walls in the wintertime when it's being pushed into those cavities onto those cold surfaces. And in the summertime or in the springtime, being able to let those walls dry out if there is any vapor in them. So that's strictly a design problem and something that we've done really great at controlling. If it's a more advanced system or more exotic, you can do Wolfie calculations. You can actually calculate how that the tendency of that vapor to build up over time or not. So I don't know, Johnny, if you want to riff on that or any good, is there a good place to go, Johnny, for more?
Well, what I would mention is that those exact problems that they're referencing that happened in the 70s led to development of materials that were first initiated in the 80s and then sort of perfected in the 90s that are airtight and vapor open. So they actually encourage drying. So we have those materials now that we didn't have then, and that's the big difference.
And I'm going to add just one more thing. This is a misconception. a leaky house is much more susceptible to having rot from moisture coming in, because air going through your wall is going to condense. It's one of the primary ways to get water into the building. Once you don't keep the rain out, the next way the moisture is going to get in is from very wet air condensing on cold surfaces anywhere inside your building envelope. So air tightness in general protects the walls from rotting. So it's kind of the opposite of what we're talking about from the 70s house. Air tightness is the only way to protect a modern house now. Or one of the best ways, I should say, not only. It's an overstatement.
So for fences, next one, for fences, which materials should be used other than wood?
Just about anything, right? Hey, we have too many damn fences, so that's a personal opinion. Yeah, I don't know. I'm not really, that's something that needs a lot more research. I know we're used to the cedar picket. I got cedar picket right here. Fencing is for the interior of my house, in fact. So I love the stuff. So think of it as like, this is not a ban on wood fences. This is just disconnect the wood fence from the house itself. Think of it as like a wick. So the last 5 feet, maybe 10 feet, have an alternative fencing system or no fence at all, but just keep that disconnect from the house to whatever the kind of the wooden structure is.
And I guess I was a little, that was just the first part of it. It looks like we have several questions about fences in general. So I'll read some of them and maybe we can riff off of that. But we need to creatively have safe spaces for pets, containing pets. Also thinking about, okay, what other possible materials could we use other than wood? And also people talking about how HOAs sometimes require wood fences and mulch next to the house, and thinking
The
about
mulch
ways to
is
get
a
around
no-go, right? The mulch is just outright zero. That you can't do that now. We know that for fire resilient design.
So that seems like something that should be approached with the HOA.
Yeah. I mean, HOAs are famous for kind of water intense landscaping, kind of very depersonalized buildings and gardens. So, and you pay for the pleasure of that. Yeah, I think we need to get lots of landscape architects engaged with this process. And I think that's going to be something a lot of people have asked about. And I would love to learn more, as well as kind of integrating Firewise, even xeriscape landscaping best practices within kind of communities, and make that just a normal conversation for HOAs.
Yeah. And one thing that got brought up is, for example, wood fence, but then an aluminum gate between fence and house would sort of be an example of what you were talking about, like separating that wick.
It's brilliant. Yeah.
Yeah.
It's probably more sturdy too, right?
But to your point, what you mentioned, xeriscaping, are you aware of plants that are good in terms of both low water usage and are Firewise?
Please ask me building questions. I don't know. All I know is I live in the woods, and all I do is cut trees down.
Yeah, so this
won't make me very popular.
That seems like something that we will definitely want to talk about. We are going to have one of our future events is going to be on specifically on fire resistant materials, and we want to make a part of that about landscaping, definitely, especially considering this conversation. So let's see. Next up, we have if 2018 IRC, that's Superior's current code, is insufficient to prevent cascading fire, what code standards or code plus design elements would be needed?
I think a lot of what we talked about, the materials, the fences, a lot of these Firewise suggested things can be codified extremely easily, and they are codified in certain areas. As we talked about before, codes in California in different areas did change after some of these very significant urban fires, like my family's situation. We went through Oakland. I think that was a wake-up call to a lot of people that entire cities can burn. So code can easily adopt to that. It's as important as that code's new, that's enforced, it's understood, and it makes sense. For instance, like if we start just forcing everybody to put in expensive things like sprinklers, but we neglect other components of the buildings, there's maybe not a balance for the overall kind of code compliance. I'm an envelope guy, so I always think of envelope first. Sprinklers inside are more of a life safety thing. Typically, like for a wildfire, they're not going to do much to protect your house. If it starts from the outside sprinklers can be very complicated and expensive. So I think there are some basic code things that have synergies with these other things, like the higher performance side. If they're going to want a all electric house, we should also look at codifying the windows to be triple paned, for instance. I'm kind of throwing that out there, but there's a lot of synergies that code doesn't necessarily recognize now that we can talk more about those synergies. So you get more bang for your buck as your house is more resilient.
And you had mentioned earlier about the difference between some 90s code and 2008 code, and that the more recent code being more resilient. Could you speak to that a little bit more?
So I'm going to say that code now, typical type 4 resident or type, sorry, what am I looking at? Type 5 residential code has almost no fire resilience components for exterior fire conditions in it. Almost nothing outside of maybe the roof material. And that's my personal opinion. Other people might have a different opinion, but most of it's life safety. It's to get you out of a burning building, to slow the fire down. It's not to resist a fire. It seems like a subtle difference, but it's not. They want a predictable time for you to escape a building, so you don't go down with the building.
Switching gears a little bit, question: Do indoor fireplaces have a place in Passive House? Are they possible? You could go electric or a faux fire, I know, but what about in terms of energy use and other options other than traditional open fireplace?
It's definitely possible. I remember the fireplace conversation with, we have somebody who built a passive house in England, and he wanted to put fireplace, and he's a very experienced, he works for a huge architecture firm that does almost exclusively passive house. So he knew what he was doing, and he had this long conversation with this other great English passive house consultant, and they went back and forth about the fireplace for years. And he put it in, and he says he never uses it. He uses it like 3 or 4 times a year because he just gets blasted out from the heat. It's just too much. And it's a tiny little fireplace, so it is passive house compliant. So that's the good news. But he spent, probably 5,000 pounds for it and never got to use it. So even for entertainment, it lost its appeal. And also, let's say like in an urban area, I think fireplaces should be probably pretty much banned at this point, because we've breathed enough smoke. Our air quality is bad enough, especially in the winter, that burning fires is kind of, maybe in other regions it makes more sense, but at least in city or the Front Range, I don't think it makes any sense anymore.
And I have heard of one of the responses I get often for this one is the vapor fireplace. It's sort of a faux fireplace. I don't know if you've ever used one of those, but they're pretty good looking now. Like they're pretty convincing. So that's another option.
Or buy a Tesla and just turn on camp mode, you know.
Camp mode? What is camp mode?
Well, they have a little fake fire on the screen when you.
Oh, yes. So next, land use, residential density, and fire resistance. Some experts say structures should be 35 feet apart. Pressure to increase ADUs on average lots will not allow distance. Also, denying screening vegetation will make ADUs and main buildings unappealing. Should we keep more distance between buildings to improve fire safety?
I laugh. No, we need to build cities. We need to do just the opposite. We need density, and we can. You know, it's not like our downtowns are burning, right? Like we know how to build controllable built environments in dense areas. In fact, the densest cities, Chicago, Tokyo, you know, famously, London, have all burned, and they've learned how to build densely in fire resilient design. So that's exactly the opposite. And in fact, that's kind of where we run into problems, where we solve one problem to create 15 more problems around what kind of transportation, infrastructure, carbon, costs, you know, even all these things get more and more acute when we don't look at density as a proper kind of end goal. So
next one's interesting. After ditching fossil fuel in my house, Excel surprised me with an outrageous estimate of $5,323 to remove my 37 feet of gas pipe and meter. Can we make removing the abandoned piping less costly and reduce fire danger if possible? That's really interesting. I've never heard that.
I've heard that. Yeah.
Really?
Sure. Yeah. Because you have to pay a monthly fee just to have the gas line fee to your house. So that sucks. I mean, the first thing is that, like, when people are building without a gas line, it saves them quite a bit of money in the first place. So they kind of, especially for new apartment buildings, things like that, they need to be individually metered. It's a huge cost to put those things in the first place. And yeah, Excel is confused, right? They're in a confused place because they want to make money by selling you fuel, but they want you to go all electric. So they don't have a clear answer on that. And I think that's something that should be brought up over and over again, especially on the retrofit side. And Excel is a public utility, so they're responsive to the public from the utilities council. They're overviewed by elected officials. So that's something that should clearly be targeted as an issue.
Can you speak more, especially since you're doing it on an upcoming project, how prefab panels can be superior to building on site?
I mean, the old joke is that we don't build cars in our driveway. You know, we built them in factories, but we tend to build houses in our driveways on site. So we bring in bunks of wood in all weather conditions, and people are out there putting these things together in inclement conditions. So once we get to passive house levels of quality control, transferring that to a factory condition saves a little bit of money, but it also improves dramatically the quality of the building, the walls themselves. And let me say, you also get to, once these panels, they're built in a factory, it's not like the whole house is in the factory. They're just the walls and the roofs and sometimes the floor. When they go on site, you can actually make them dried in, we call it. So you can make it weather resilient within just a couple of days, maybe 3 or 4 days at the worst. And some of these things, like some of the products that 475 does for exterior, can be out exposed for 6 months or longer. So we in the elements before we cover them with siding or roofing. So it just helps the process quickly. It also kind of moves the stack back so we don't need building crews stacked on location. We can bring in the plumbers and electricians and finishers relatively quickly rather than waiting for these kind of conditions to be built on site. So basically you have an exterior that is rain, water resistant. You have the structural elements, the framing side, you have the insulation and the airtight interior, and typically a mechanical chase for the passive house panels inside of that. So it's great. We're trying to do every project we can right now with that type of system.
Next one, what are your thoughts on all steel homes? And I'm going to assume by that meaning all steel siding on your home. So
I don't know. I wouldn't assume that, but like steel studs are not necessarily that much better than wood in some ways. And it's the interior house that you have to protect as well. So, and steel studs conduct heat like crazy. So not great. But we don't see that too much.
Well,
residential.
It reminds me, the example that keeps, one of the examples that keeps coming up when we talk about this is the video from Jay Leno where he talks about they spent a lot of money building a completely fireproof garage for these expensive cars, only to find after a fire that the structure survived and the interior was completely melted. Literally, the cars melted.
Yeah.
And so I think that's part of what you're getting at there is that definitely, even if we go into great lengths to make this structure completely flame resistant at a certain point, the interior will still be lost.
You know, for siding, I love steel siding. I just finished a project that was mostly all steel siding, and it looked great. It's more modern, more contemporary, of course. But boy, it's neat to see that come more back to vernacular. And then on kind of, we're talking residential, but more on the commercial side for larger buildings, looking at steel buildings, often the point of failure is the connections of the steel gets really soft around 600-700 degrees. So just for like the survivability of a building, for life safety, steel buildings are somewhat vulnerable structurally in fire events, which is kind of fascinating. So it's a really complicated topic.
Next up, let's see. How do we detail new eaves or renovate existing eaves to make them more fire-wise? If they aren't vented, how do we design to resist moisture damage?
That's another complicated topic. And this is where code runs into reality. Is the code typically wants a ventilated roof assembly, or they want a certain amount of insulation exterior. And this is where if you have a ventilated roof now in an existing house, keep it ventilated, and you can put in these fire resilient vents. Essentially, you can Google. They're pretty easy to find. What they do is they make kind of this long track for the embers to get through. So hopefully within a screen, hopefully the embers can't pass through them within a fire event. If you're doing a new build, I really highly recommend, this is where the airtightness thing comes again. It becomes that vapor control. So we're keeping the vapor from getting into the attic and getting into the underneath the roof, essentially, in condensing there. So we're controlling the rotting situation from there. And as I said, code is difficult when it comes to roofs, infamously, because code just requires having that cold air come over that roof for a ventilated thing, and that can work sometimes, and other times they can lead to moisture buildup compared to a properly detailed interior. So I can't, I wouldn't want to hang my hat on one particular thing. Ask a professional for sure. Every situation is different. And for retrofits, definitely do not do major roof changes before you talk to somebody who looks at the building really detailed in a detailed fashion.
Harkening back to your explanation of the sticks versus logs, we know that older homes in downtown, homes built from large timbers, are more fire resistant. So should we consider that as an option or a portion of the home?
I don't think so, not with a modern wall assembly where you have those insulation materials in there that will keep essentially oxygen from the framing. But when you start looking at like a mass timber type of building, you may be onto something. There's clearly mass timber. Mass timber is when you have either large timbers like 6 inches, 8 inches in as a framing system, or you're looking at something called LVLs or CLTs, cross-laminated timber construction. Big slabs of wood are extremely fire resilient, ironically, and used extensively now in large building construction. But you still need a place for insulation. You're going to end up with lots of sticks of wood in a typical house, even if it's not the structural part. So,
and another thing that I've heard before referencing these older homes is that a lot of older homes was built with old growth wood and larger old growth wood beams that just have a harder time burning, period. We just don't have access to that type of lumber anymore.
yeah,
Well.
I've heard like Ipe wood and things like using really hard woods for decks was fire resilient. And I think Matt Reisinger, somebody tested that and they found that old growth burns pretty good.
Really?
Yeah. So I think it was the dimensional quality of it, like the 2x or the 5/4 size. But I wouldn't hang my hat on having a slightly larger piece of old growth lumber to be any level of protection, to be honest.
Can you speak next to the different levels of Passive House certification again? What does the certification process look like from your experience?
It's a lot of QA. So the first thing is
QA meaning
quality assurance. So kind of the heart of it is that it's a performance standard. We talk about that all the time, but that performance standard is constantly evaluated through the building and design process. So that's why there's all those people are important ingredients of it from the certified passive house designer. You can do a passive house. I did a passive house without anybody certified. I did have one person who was supposedly helping me with the energy modeling who was certified, but that didn't help, to be honest. So, all the guys on the gang were not certified. We were learning as we go, and we're in a better situation now that we have lots of excellent trainings and lots of good houses, projects on the ground. So you just have to know at the very beginning that that's what your goal is, to certify it. Do not design a house and then say, how do I get this certified? I've tried to consult. I've given up on consulting because that's what people want to do. And it's never been a happy outcome. So always first state to your goal. And that's why the owner is so critical to this, that's what your goal is. And then assemble that passive house team. And that's totally doable. I have passive house architects calling me who are interested in doing projects in Colorado. We have a lot of people who are interested in building passive house. We have a total ecosystem now too. So it's completely within reach, I should say. I don't know if that answers the question because it's a longer format kind of thing. And there's a video that the Colorado Renewable Energy Society will be coming out. The talk I gave last week on more on the passive house process that they can probably share.
That would be nice. Yeah. I mean, one vital part that I would want to mention is, as opposed to standard construction, is the modeling and the forethought that goes in before you build one bit of the building. Is that the process has been sort of determined ahead of time is pretty vital. If you start deciding that it's going to be a passive house after it starts being built, it's almost impossible.
I don't know of many projects that made it that way.
Mhm.
And a lot of people, when they first start a passive house, they make decisions that are kind of referenced based on their past knowledge. So it's really good. We have a network. It's really good to have conversations with passive house people in general around, not just the players on the team, but just keep those conversations going. It's very complicated. Buildings are complicated to begin with, even though we try to quote unquote dumb them down. But passive house adds a whole new like dimension. I'm going to say it's not just another kind of set of rules to the side. It's a dimensional thinking about the building design process. So that's kind of why it's been so intriguing to people, so that it's changed the way that we approach the building process in the first place.
So the next one, which I think we're going to wrap it at this, it looks more like a statement. So I'm just going to read it out, but code allows unvented roofs, and retrofitting to an unvented roof is allowed. You still want the eave for water protection. Code allows all the fire hardening of structures. It just doesn't make it mandatory. Code is not bad and needs to be understood.
Well, code is the least legal building you can build. So you can start it from that point of view. It's saying that this is, if you build anything less than this, it's an illegal building. And there's a lot of different reasons for how that came into being. It's good to hear that, yeah, as far as retrofits can be complicated. You can definitely build, so you can absolutely build a unventilated roofing system. Minimum is terrible. Minimum, what else do you do in your life that's minimal? Let me ask, when you bought your car, or when you go to the grocery store, do you buy the minimal when you buy clothes? We can't treat our buildings like that, right? To me, that's my personal opinion. So I think we need to like really kind of, it's very personal. You're building buildings that are going to last generations, and I'll leave that code is kind of this weird. It's not performance-based, it's compliant-based. Even when they have what we call a performance-based code, it's not really performance-based. It's really taking all these kind of different areas of building science or vernacularism or kind of best practices, and it's putting it in definite terms, but they don't necessarily merge together. And they can either create conflicts, or they don't necessarily create the best outcomes necessarily. So what we're proposing that we can provide better outcomes by looking at buildings in a kind of more complete fashion as systems, rather than kind of components layered on top of each other. I guess that's kind of my approach to dealing with code.
Well, we're going to wrap there. Thank you everyone for coming. Thank you, Andrew, for putting this together. Thank you to our interpreters for interpreting. Thank you all, and good night.